So, remember that moment? Feels like yesterday, but also ages ago when ChatGPT just sort of burst onto the
Oh,
scene.
absolutely. Total whiplash.
Yeah, I felt like everyone just stopped and went, "Wait, what is this?" The disorientation was real, but so was the excitement, you know?
Definitely.
And what really surprised me, and I think a lot of us, wasn't just like what it could do, but the sheer explosion of new ways people started using it. It
Yeah.
wasn't just another small step for AI models. It felt like a leap. So, okay, how did we get here? How did we go from fancy autocomplete to, well, this?
Well, what's fascinating, right, is that the AI community, they kind of knew for over a decade that just making models bigger would make them better.
Okay.
I mean, way back in 2012, the AlexNet paper guys, huge moment in deep learning. They basically said, yeah, results get better if you just wait for faster GPUs and more data.
Huh. So it wasn't a total secret sauce.
Not entirely.
Hmm.
But like you
Yeah.
said, the scale of applications this latest jump unlocked. That was the real surprise. So yeah, this deep dive, it's basically a shortcut. We want to get you up to speed on the essentials of building these generative AI systems, these foundation models.
Cutting through the noise a bit.
Exactly. Cut through the hype, find the stuff that actually lasts, the foundational knowledge, helping you figure out what really matters in this super fast-moving space.
And honestly, making sense of it all, Chip Huyen's book, AI Engineering, has been, well, fantastic. It's like a really solid map through this complex territory.
It's a great resource, definitely.
Now, when we talk about this rapid rise, it's not just a gut feeling, is it? The numbers are kind of mind-blowing.
They really are.
AI engineering has seriously become one of the fastest, maybe the fastest growing engineering fields out there. I mean, get this. In just 2 years, 4 open source AI tools, AutoGPT, Stable Diffusion Web UI, LangChain, Llama, they've already racked up more stars on GitHub than Bitcoin. And they're apparently on track to blow past even huge web frameworks like React and Vue. That's just incredibly fast adoption.
It absolutely is.
Yeah.
And if you connect that to the bigger picture, it highlights something really important.
Okay.
While, yeah, some core ideas for building AI apps haven't changed, the sheer scale and the power of these new models, they bring totally unique opportunities,
good.
but also unique challenges.
So it's not just old wine in new bottles.
Not at all. It demands completely new solutions. This isn't just a new buzzword, AI engineering. It's a genuinely distinct field shaped by these powerful general-purpose models. It's different from traditional machine learning, which often focuses heavily on, say, tabular data,
Yeah.
crafting features by hand, training specific models.
Right, more specialized tasks.
Exactly. AI engineering. It's all about prompt engineering, building context, parameter-efficient, fine-tuning stuff that's crucial for these big foundation models.
Okay, so let's trace that journey a bit. From those earlier language models to what we now call foundation models. What was the key breakthrough that really let them scale up and get so powerful? I'm thinking about this self-supervision idea. What actually is that?
Yeah, great question. And it really was an evolution. But that single biggest breakthrough, probably self-supervision, it basically solved the huge bottleneck of needing humans to label data.
Ah, okay, so they learn on their own.
Kind of. Instead of needing explicit labels, the model figures them out from the input data itself. Think about a simple sentence like, I love street food.
Okay.
With self-supervision, that one sentence gives you multiple training examples. The model can try to predict love just from seeing I, or predict street from seeing I love, and so on.
So it slices and dices the sentence?
Pretty much. You get maybe 6 training examples from that one little phrase.
Yeah.
This trick, making the data kind of label itself, it's arguably the crucial innovation that let AI break free from needing so much human input and scale like crazy. Turned models from niche tools into these general powerhouses.
And I remember, back when OpenAI's first GPT came out, 2018, 117 million parameters seemed massive.
It's huge at the time.
Then GPT-2, 2019, 1.5 billion parameters. Suddenly, 117 million was, tiny. It's wild how fast large changes.
It really is. I mean, when the book was written, 100 billion parameters was considered large. Who knows, maybe one day that'll seem small too.
Probably.
But what's really key here is how foundation models go way beyond just text now. Early language models, text only. Foundation models, they pull in images, video, 3D stuff, even protein structures.
So they're multi-talented.
Exactly. Truly general purpose, not task-specific. Like an LLM can do sentiment analysis and translation before you need totally separate models for each job.
So what's actually going on inside these models then? When we talk about design and training, I hear about 2 main stages. pre-training and post-training. What's the difference? Why do you need both?
Right. So pre-training is phase one. That's where the model becomes capable. It learns from just enormous amounts of data using that self-supervision trick we talked about.
Okay, learns the basics of language, patterns, etc.
Exactly. But a pre-trained model, it's not necessarily safe or easy to use straight away. It might just complete text, not answer questions properly, or it might parrot biased or harmful stuff it found online.
Ah, right, because it just hoovered up everything.
Pretty much. That's where post-training comes in, phase two. The goal there is to align the model with human preferences, teach it to give appropriate answers, filter out the bad stuff, be helpful.
Yeah, got it. So pre-training for capability, post-training for usability and safety.
You got it.
And that initial training data, the stuff it hoovers up, its quality must be super important. You mentioned English dominates the internet, so models are better in English. Can you give an example of that gap?
Oh, absolutely. It's quite stark.
Yeah.
Take the MMLU benchmark. It covers like 57 different subjects.
Yeah.
GPT-4 does way better in English compared to languages that just aren't represented as much online, like Telugu. And for math problems, GPT-4 solved English ones over 3 times more often than problems in Armenian or Farsi. And for languages like Burmese or Amharic, it completely failed.
Wow. Just could we do it?
Mostly because there just wasn't enough data in those languages in its training set.
Yeah.
Language structure, culture, those can play a role too, but data representation is huge.
And that affects even specialized models. Like, didn't Bloomberg make one for finance?
Yeah, Bloomberg GPT. But what's interesting is, even though it's specialized, a general-purpose model like GPT-4 can sometimes outperform it on finance tasks.
How?
Just the sheer scale. The massive amount and variety of data, plus the huge compute power used to train GPT-4, can sometimes overcome the specialization. And underneath all this, architecturally speaking, is the transformer model.
Right, the attention mechanism.
Exactly, that core idea. Think of it like the model figuring out which words in a sentence are most important to pay attention to when it's trying to understand or generate the next word.
Yeah.
It uses these internal signals, query, key, value, to weigh that importance. Super clever.
Okay, so progress has been insane, but I'm hearing whispers, concerns growing behind the scenes. We're actually hitting some, surprising roadblocks to scaling AI even further. What's going on?
Yeah, there are a couple of big ones emerging. The first one, and maybe the most surprising, training data.
We're running out of internet.
Kind of. Foundation models eat data so fast, there's a real worry about running out of high-quality data online in the next few years. Training data sets are growing way faster than humans are generating new text and images.
Huh. I never thought about that.
And there's another twist. The internet is now getting flooded with AI-generated content.
Oh, right. Models trained on the output of other models.
Exactly. And if future models just keep training on this synthetic data, there's a risk of something called model collapse.
Model collapse? What's that?
It's where the models gradually forget the original patterns from human data and just start repeating the patterns from AI data. Their performance degrades over time. It's like making copies of copies of copies. Eventually, the original gets lost, or worse, turns into nonsense.
Like an AI echo chamber.
Precisely. And this makes proprietary data stuff like copyrighted books, medical records, internal company docs suddenly incredibly valuable, a competitive edge.
Which is why Reddit and Stack Overflow are locking down their data.
That's a big part of it, yeah. They don't want their valuable human-generated content scraped for free to train competitors.
Fascinating. And kind of worrying for open source or smaller players, maybe? Does it create a huge barrier? And what was the second bottleneck you mentioned?
It definitely raises questions about who can really play at the cutting edge. The second bottleneck, electricity.
Power.
Yep. Less obvious, maybe, but potentially even more serious. Data centers already use something like 1–2% of global electricity.
That sounds like a lot already.
It is. And projections, they estimate it could reach anywhere from 4% and maybe even 20% by 2030.
20%.
Yeah, it raises real concerns about power shortages, which would obviously drive up electricity costs.
Yeah.
Just to give you some context, one NVIDIA H100 GPU, a high-end AI chip, running flat out for a year, it uses about 7,000 kilowatt hours.
Okay. How much is that?
Well, the average U.S. home uses around 10,000 kilowatt hours in a year.
Wait, so one GPU uses almost as much power as an entire house.
Pretty close.
Yeah.
Now imagine data centers packed with tens of thousands of these. It's almost mind-boggling. Makes you seriously wonder if our power grids are actually ready for this AI boom.
Okay, switching gears a bit. These models, they're fundamentally probabilistic, right? Which is why they're creative, sometimes fun, but also why they do weird stuff. Can you unpack sampling and those settings like temperature, top K, top A? How do they work?
Sure. So at its heart, a model generates text token by token through sampling. You give it input, it calculates probabilities for every possible next word or piece of word.
Okay.
Temperature is like a knob that controls randomness. Higher temperature, the model gets more adventurous, picks less likely tokens, more creative maybe, but potentially less coherent, goes off the rails.
Can they stuff up more?
Could do, yeah. Lower temperature, it sticks to the most probable, safest choices, more consistent, predictable, but maybe kind of boring.
Right. And top K, top K.
There are ways to limit the choices. Top code just says only pick from the top cuck most likely options. Top cube, or nucleus sampling, is a bit smarter. It picks from the smallest set of options whose probabilities add up to at least p, so it adapts based on how confident the model is.
Got it. And this probabilistic stuff, this randomness, it directly leads to two big frustrations people have: inconsistency and hallucinations.
Exactly right. Inconsistency is just, you ask the same question twice, you get two different answers. Can be confusing, like if I called you a different name every time we met.
Right, unsettling.
And hallucinations. That's when the model just confidently makes stuff up, states things as fact that are totally wrong.
Why do they do that? Is there a theory?
A leading hypothesis is that they basically can't tell the difference between the information they were given in the prompt and the information they've generated themselves during the response.
Huh. So they believe their own generated text.
Kind of. Like, if you ask, who's Chip Huyen? And the model happens to generate Chip Huyen as an architect, it then treats Chip Huyen as an architect as a known fact when it generates the next part of the sentence.
Oh, wow. It builds on its own fictions.
Exactly. Like a really confident friend who tells tall tales and then forgets they made them up. Starting just a little bit wrong can snowball into something wildly inaccurate.
Is there any way to stop it?
No magic bullet yet. But asking for concise answers helps. And being really specific in your prompts can sometimes reduce the chances.
Okay, so putting this all together, what does it mean for you, the listener? For your business, maybe your daily life? These foundation models are general purpose, right? So apps built on them can tackle a huge range of problems. What are some cool examples?
Oh, tons. Take education. AI is really shaking things up there. It can summarize textbooks, create personalized lecture plans for individual students, generate quizzes. Khan Academy even has AI teaching assistants now.
I saw that. Pretty amazing.
And the impact. Remember Chegg, the homework help company. Their stock price tanked right after ChatGPT launched because students just started using AI instead.
Wow, that's a direct hit. Shows how fast things are changing.
It really does. Then you have conversational bots. Everything from general chatbots and AI friends to serious enterprise customer support bots that can actually file insurance claims or walk users through tricky processes.
Yeah, virtual agents.
Exactly. Researchers are even using groups of bots to simulate whole societies to study social dynamics. It's wild.
Here, what else?
Information aggregation. Summarizing your emails, Slack threads, news articles, talking to your documents. Salesforce did research in 2023, 74% of generative AI users use it mainly for summarization.
Makes sense. Saves a lot of time.
Totally. Think Google Photos, understanding your pictures, or image search, finding things visually. And finally, workflow automation. Automating simple stuff like booking a restaurant or planning a trip, but also complex business tasks like managing sales leads, handling invoices, data entry.
Okay, so you've got these incredibly powerful general models, but you need them to work for your specific thing. How do you customize them? This is where you hit that big decision, right? Fine-tuning or along? Retrieval Augmented Generation, RA.
That's the core choice, yeah. And there's a simple way to think about it. Fine-tuning is mostly for form. RAG is mostly for facts.
Form versus facts. Okay, break that down. Fine-tuning.
Fine-tuning means actually changing the model's internal parameters, its weights. You're adapting the model itself. It takes resources, data, compute, but it's great for teaching the model specific styles or syntaxes.
Like if you wanted to always output perfect HTML code.
Exactly. Or speak in a very specific company voice or understand a niche technical language. And there are techniques now, like parameter-efficient fine-tuning. PEFT LoRa is a popular one. Low-rank adaptation. Basically, instead of tweaking all billions of parameters, you only update a small fraction. Makes fine-tuning much lighter, more accessible, less memory-hungry.
Okay, so fine-tuning shapes the model's behavior and style. What about RAG, and how do you pick?
RAG, Retrieval Augmented Generation, is different. It doesn't change the model itself. Instead, it retrieves external information from your documents, databases, whatever, and feeds it to the model along with your prompt.
So it gives the model cheat sheets.
Kind of. It makes the responses more accurate and up-to-date by giving it relevant context on the fly. It's perfect when tasks need lots of background knowledge that won't fit in the model's limited context window. Think huge code bases, medical research papers.
How does it retrieve that info?
Two main ways. Old school, term-based retrieval, like keyword search, think BM25 Elasticsearch. Or newer embedding-based retrieval, which uses vector databases like FACE or HNSWD to find semantically similar information. Stuff that means the same thing, even if the words are different.
And people use tricks like chunking data smartly, rewriting queries.
Exactly. All to make the retrieval better. So the decision. If your model has issues with both what it knows, facts, and how it behaves, form style, my advice is usually start with RAG.
Why RAG first?
It's generally easier to set up. You don't have the headache of curating lots of specialized training data or the cost and complexity of hosting your own fine-tuned models. Our RAG can fix the information gaps quickly. Then you can see if you still need fine-tuning for the behavior. Knowing which tool to reach for first is key.
That's a really clear distinction, form versus facts. Super helpful. Now, let's tackle what you called maybe the hardest part of AI engineering evaluation.
Ah, yes, the big challenge.
Because lots of people faced with judging an AI's output kind of default to word of mouth or just a vibe check. Does it feel good? Which isn't exactly rigorous science.
Not really, no. A vibe check doesn't scale and isn't reliable.
So if the vibe check isn't enough, how can we systematically measure what good actually looks like for AI?
It's tough. You start with some basic metrics. For language models, there's perplexity lower is generally better. It means the model is less surprised by the text. But it gets weird after post-training sometimes. Then you have similarity scores, simple word overlap, or deeper semantic similarity using embeddings.
Okay, but that feels a bit surface level.
It can be, which is why the conversation gets really interesting when we talk about using AI as a judge.
Wait, having AI judge other AI, doesn't that feel a bit circular? Like asking a student to grade their own homework? How do you stop it just reinforcing its own biases, especially for creative stuff?
That's a valid concern, the tautological aspect.
Yeah.
It can reinforce biases, but AI judges has upsides. They're flexible. You can ask qualitative questions like, does this response sound like Gandalf? Or rate things like trustworthiness. They're also consistent, which humans aren't always.
But there are downsides too. Cost, maybe?
Yeah, cons are, it's not standardized. It adds cost and latency to your evaluation pipeline. And well, AI judges can be wrong. Remember Microsoft's Tay chatbot going off the rails? Or Google AI search suggesting people eat rocks?
Oh yeah, the Ross eating thing. Yikes.
Right. Underscores you need robust evaluation, whoever the judge is. Generally, AI judges work better when you ask for classification. Is this toxic at a yes, no?
Right.
Or discrete scores, like 1 to 5, rather than asking for a continuous score.
Okay, so AI judging AI is one way. What about comparing models against each other?
That's comparative evaluation. Think of leaderboards like the LMS-YS chatbot arena. They rank models using pairwise comparisons, showing users 2 responses and asking which is better. It's like chess ELO ratings, but for chatbots.
That seems powerful for picking the best overall model.
It is, but there's a really crucial point here. Preference isn't always the right measure.
How so?
Well, if you ask a factual question, you want the correct answer, not just the answer someone prefers, right? Preference might lean towards longer, more confident-sounding answers, even if they're wrong. So correctness matters too.
Good point. So beyond judging, what are the key things we evaluate?
We look at factual consistency. Does the output contradict itself or known facts? Methods like SAFE break down responses into individual facts to check them. Textual entailment checks logical consistency. We absolutely evaluate safety, looking for toxicity, bias, harmful content. We check instruction following. Does it obey formatting rules, stay on topic? Benchmarks like iFeeble and InfoBench help there. And then, always, the basics. Performance metrics like latency and cost. How fast is it? How much does it cost to run?
Okay, building on that, let's talk AI agents. This sounds like the next level. Systems where the AI isn't just responding, it's acting like a brain processing info, planning actions, deciding when a job is done, moving way beyond just Q&A, right?
Absolutely. Agents are about giving AI more autonomy to achieve complex goals. Architecturally, they have a few core parts. They need planning abilities.
How do they plan?
Often through prompting techniques like chain of thought, where you literally tell the model, think step by step. They also need memory.
Memory, like remembering past conversations.
Yes, but more than that. There's the internal knowledge from training, there's short-term context, like the current conversation, and crucially, there's long-term storage, so an agent can remember things across many sessions. Think of an AI coach remembering your goals and progress over months.
Wow. Okay, planning, memory, what else?
Tools. Agents need to interact with the outside world. So
Understand.
tools could be web search access, the ability to run code, query a database with SQL, check an inventory API, book a flight.
So they can actually do things.
Exactly. And a key concept in making agents work well is this action plan reflection loop. Frameworks like Reflection implement this. The agent tries something, sees if it worked, reflects on errors, and updates its plan for next time. It learns from mistakes.
So they can learn and adapt. That raises a huge question, though. Can these large language models, these LLMs, actually plan in a deep sense? Or are they just really good at pattern matching what planning looks like from all the text they read?
That is a huge debate right now. Experts like Jan LeCun are pretty skeptical, arguing that current autoregressive LLMs, which just predict the next word, can't genuinely plan ahead. They might just be retrieving and stitching together planning-like text they've seen before. Others are more optimistic. It's a really active area of research.
Fascinating and crucial for how far these agents can really go. Okay, so we've built this amazing AI, maybe even an agent. Now, the practical bit. How do we make it run fast and affordably in the real world? What's involved in the operational layer?
Right. Got to make it work reliably and efficiently. This brings us to inference optimization. Key distinction here. Training is building the model, takes ages, costs a fortune. Inference is actually using the model to get answers. That needs to be fast and cheap.
Okay, and how do you measure inference speed?
Two key metrics usually. Time to first token, or TTFT. How quickly does that first word pop up? Really important for user experience. Feels responsive. And then time per output token, TPT. How fast do the rest of the words stream in? Crucial for longer answers.
And how do you improve those at the model level?
Several ways. Quantization is a big one. Reducing the number of bits used to store each parameter value. Like Microsoft's BitNet B1.58 uses just 1.58 bits per weight, but performs like a 16-bit model on smaller scales, saves huge amounts of memory and speeds things up.
Wow, 1.58 bits. That's tiny.
It's amazing what they can do. There's also speculative decoding. Use a small, fast draft model to guess the next few tokens, and then the big, powerful target model just quickly verifies them. Much faster than having the big model generate every single token itself.
Clever. And what about optimizing at the service level when you've got lots of users hitting the model?
Yeah, service level optimizations are key. Batching is common. Processing multiple user requests together in one go, more efficient for the GPUs, increases throughput, and prompt caching. This is huge for chatbots.
Prompt caching, storing parts of the prompt.
Exactly. If parts of the input are repeated across requests, like the system prompt, you are a helpful assistant, or long document users are asking questions about, you cache the model's internal state for that part.
So it doesn't have to reprocess the same text over and over.
Right. It can dramatically cut latency, especially time to first token, and save a ton on costs because you're processing fewer tokens.
Right.
For instance, caching a 100,000 token book can cut TTFT by almost 80% and cost by 90%. Huge gains.
That's massive. Okay, so how do all these pieces, the model, RG, maybe optimization techniques, fit together in a typical AI engineering architecture? It sounds like it could get pretty complex.
It can start simple. Just a user query, go into the model, getting a response back. But then you start adding layers for robustness and features. First, almost always, guardrails.
Guardrails, like safety checks.
Exactly. Checking the input before it hits the model for harmful content, prompt injection attempts, and checking the output before it goes to the user for toxicity, sensitive data leaks. PII masking is common here, spotting things like phone numbers or credit card numbers, often using dictionaries of common patterns and hiding them before sending data to external APIs.
Makes sense. What comes next?
You might add model routers or gateways if you have multiple models or complex workflows, routing requests to the right place, handling security. You'd likely implement caching, both exact match caching and maybe semantic caching, storing results for identical or similar queries.
To avoid recomputing answers.
Right. And then, if you need more complex behavior, you integrate those agent patterns we talked about with planning, memory, and tools.
Okay, so you've built this sophisticated system, lots of moving parts. How do you keep track of it all? Know if it's working, debug when it breaks. This must be where monitoring and observability become vital.
Absolutely crucial. You can't fly blind with these complex systems. You track key metrics, things like factual consistency scores, toxicity rates, latency, cost, transactions per second, TPS.
But numbers only tell you so much, right?
Exactly. Metrics tell you what happened, but not always why. That's where logs and traces come in. Tools like LengthMyth let you trace a single request step by step through your entire system. See the prompts, the RAG results, the intermediate model calls, the final output. Invaluable for debugging.
like an X-ray into the system.
Good analogy. And then there's drift detection, monitoring how the inputs users are sending or the outputs the model is generating change over time. This can flag subtle problems, shifts in user needs, or maybe indicate your model needs retraining.
Okay, last piece, but maybe the most powerful in the long run. Imagine the people using your AI aren't just consumers, they're actively teaching it, making it better just by using it, closing the loop. How does user feedback become this amazing engine for improvement, this data flywheel?
It's potentially the biggest competitive advantage. User feedback is unique, proprietary data. It fuels this data flywheel. Use the app, provide feedback, use feedback to improve the model. Improved model leads to better app, which attracts more users who provide more feedback, and round it goes.
How do you capture that feedback, explicitly asking?
That's one way. Explicit feedback, thumbs up, down buttons, star ratings, a direct question like, was this helpful?
But there's also implicit feedback.
Implicit, meaning you don't ask directly. Right. You infer it from user behavior. Did they rephrase their question after getting an answer? That suggests the point answer wasn't good. Did they copy the AI's code snippet? Probably means it was useful. Did they click on a suggested link? That's positive signal. You watch how they interact.
Clever. But how do you design these feedback systems well? You don't want to annoy people constantly asking, was this good?
Yeah.
And you need useful data.
Strategy is key. You need to decide when to ask. Maybe only ask when the model itself signals low confidence in its answer. Google Photos does this. If it's unsure if a picture is a cat, it might ask you.
Ah, smart. Ask when you're most likely to be wrong.
Exactly. Or you can use comparative feedback, show two different responses, and ask the user which is better. That gives really strong signal for preference fine-tuning later. But you have to be aware of feedback biases.
Biases in the feedback itself, like what?
Oh yeah, humans are biased. There's leniency bias. People often rate things positively just to be nice or to finish a task quickly. Easier to click good than explain why it was bad.
Guilty as charged sometimes.
We all are. There's position bias. People tend to prefer the first option they see in a list or comparison. And preference bias, for example, studies show people often prefer longer, more verbose answers in comparisons, even if the shorter one is actually more accurate or helpful. Length is just easier to judge quickly than subtle accuracy.
Wow. So the feedback itself isn't pure truth.
Definitely not. It raises a really important question for anyone building these systems. How can you design your feedback mechanisms to truly capture what matters, knowing about, and maybe even accounting for these very human tendencies?
What a journey. Seriously, we went from that initial, whoa, ChatGPT moment, that feeling of possibility, right through to the rise of AI engineering as a real discipline.
Yeah, unpacked the models themselves, how they evolved, self-supervision, pre-training versus post-training, those big bottlenecks like data and electricity.
Right, and then into the nitty-gritty. Building apps, use cases everywhere, that key choice fine-tuning for form, RI for facts, and evaluation. Wow, that's a tough one. AI judges, comparisons.
Don't forget agents, planning, memory, tools, and then making it all work, optimization, architecture, monitoring.
And finally, closing that loop with the data flywheel, using feedback but watching out for those sneaky biases. It's a lot.
It really is. And if we just pull back for a second, think about everything we covered. The potential for model collapse, of AI eating its own tail, the massive energy needs, the deep question about whether these things can really plan. Given all that, the incredible progress, but also the real limitations still out there, what unsolved problem in AI engineering are you, listening right now, most fired up to tackle? How could you take these kinds of insights and use them to push things forward?
That's a great question to leave people with.
Yeah. We really hope this deep dive gets you thinking and encourages you to keep digging, keep innovating. It's such a dynamic